Here we are. We're going to take up the RC parallel circuit today. Standard circuit, AC power source, input voltage 115 volts with a frequency of 60 hertz. We've got a resistive, well, that's a resistive branch, 63.1 ohms, as well as a capacitive branch, but we've got a capacitance of 25 microfarads. Looking at the chart, you can see all of the given values, and I've got an awful lot of empty spaces here. We're going to go through the whole process of how to fill this in. First things first, given what I've got to work with, I can't go anywhere. I can't find impedance until I actually convert this value of capacitance into capacitive reactance. Let's go down to the board. Grab a pen, pencil, some paper. Don't forget your scientific calculator, and we're going to go through this. Step 1, determining the value of capacitive reactance. Here's the form that we're going to use. 1 over 2 times pi times the value of frequency times capacitance. Now, a lot of people kind of get hung up on this, and I've got a surefire way of making things as simple as I can make it for you. First things first, take my marker, my cheat sheet, and let's get started. Now, putting in our values, 2 times 3.1416 times the frequency, 60 hertz, multiplied by the value of capacitance. Now, this formula, we have to convert this into base units. Right now, we have a value of 25 microfarads, but that's in micro. We're going to have to do a conversion into the base unit of farads. And so this is why I put a bracket in here, is 25 microfarads divided by a million. Then we take our marker, we draw a long line, 1 over. Now, I put the brackets because of the fact PEDMAS rules. If you were to try and input this in one equation, if you don't put the brackets, you're not going to get the right answer. I would input this as 2 times pi times frequency times, open the brackets, 25 divided by 1 million, close the brackets, I would hit equal. Then I would hit the 1 over function on my calculator, and that should give me my answer. Now, there is a bit of a shortcut too. Because of the fact 2 and pi are constants, and as well, we're doing these calculations in North America, the frequency is pretty much a constant. If you punch this into a calculator, you're going to have a constant value of 377 multiplied by 25 divided by a million. Executed properly, the answer you should get 106.1 ohms of capacitive reactance. Now we're going to take this, I'm going to put it in the chart, and then we're going to keep cracking on. I've just finished inputting my value for capacitive reactance. Together with the given value of resistance, I can use capacitive reactance and resistance in order to calculate circuit impedance. So that's going to become step number 2. So I'm going to move down the board, and I'm going to just keep moving on. We've moved on to step 2, calculating the value of impedance for the entire circuit. Now, this brings us to this formula. Now, we've encountered a formula like this before, but what has changed is just that we're calculating for the value of capacitive reactance. I'm going to go ahead and input the values that we've got from our circuit. So if I put in 1 over 63.1 ohms squared plus, can't forget that PEDMAS rule, 106 ohms of capacitive reactance, 1 over squared square root, and overall 1 over. Now I did put out a short video of how to input these values into a calculator. If you haven't already done so, go into your course Moodle page and check it out. Putting all this into a calculator properly, you can do this in one equation, and the result should be 54.23 ohms, and again, this is a value that's been rounded to 2 decimals, which is standard in the electrical program here at Cambridge College. Now that I've got impedance, I can use this to calculate the current for the circuit, but I normally will complete all of the missing values for each component in the circuit before I try and solve for the entire circuit. Okay, I've got impedance and I've got an applied voltage. I'm tempted to do this, but I know better. I'm going to go and solve for all the missing values in the resistive branch of this circuit, and then I'll proceed to working on the capacitive branch of the circuit. Our applied voltage of 115 volts, this is parallel, and one of the rules that governs a parallel circuit is that the applied voltage will be the same across each branch of the circuit. So if I've got 115 volts here, I've got 115 volts down this branch, as well as 115 volts down this branch. I could easily take this value and input it right here. Same thing applies here. Well, now that I've got two values, it's simply using Ohm's law, where I could calculate for the missing value of current in this branch. And that's what I'm going to do next. Once I have this, though, I'll actually have a value in my calculator that I can actually skip to the next missing value and calculate for the value of power in watts. So that's where I'm going next. I'm going to erase the board, set up, and we're going to do steps 3 and 4 consecutively. Here in our third step, solving for the current draw of the resistor, as I said previously, we're going to use Ohm's law. We're going to take the voltage down that branch and we're going to divide it by the value of resistance. Let's take the values that we have, which is 115 volts divided by 63.1 ohms. Simple calculation, you should get for an answer 1.82 amperes. Now, I've got this in my calculator. I want to proceed to step 4 right away because that value, it's in the calculator. I want to be quick, I want to be efficient in my work, so I'm going to jump to step 4. Step 4, find the true power of the resistor. Resistors are absorbing true power, and we're just using Ohm's law where power is equal to the voltage of the branch multiplied by the current draw of the resistor in this case. So we use these values. 115 volts multiplied by the current 1.82 amperes. My power in watts is going to be 209.8 0.59 watts. Now, I've calculated everything that was missing for the resistive branch. I'm going to go and input this on the chart, and then we'll discuss what our next move is. Now, everything has been filled out for this branch. I've got the remaining branch, the capacitive branch, where I'm going to basically repeat the exact same thing. I'm going to use the voltage and the capacitive reactance to calculate the current draw. Using this value, it'll allow me to calculate the amount of reactive power. So I'm going to move down, and we're going to be doing steps 5 and 6 consecutively. Moving on to step 5. Solve for the current draw of the capacitor. Straight up Ohm's law. To find current, we're going to take the voltage and we're going to divide it by the value of capacitive reactance. In this case, 115 volts divided by 106.1 ohms. This should give you, for an answer, 1.08 amperes. Now that I've got this equation completed, you probably still have this in your calculator, and you want to move on to the next step, which is step 6. Using both of the values, the given value and the calculated value of current, 115 volts multiplied by 1.08 amperes is going to give us, as a result, 124.2 volt amps reactive for the capacitive. So I'm going to shoot down there, record it in the chart, and we're going to just keep going. Here, I've got the remaining values filled in for our capacitive branch. Now, we're going to turn our attention to the entire circuit. That means, first order of business, I'm going to calculate the value of current. From there, we're going to calculate VA, and then we will continue with circuit efficiency, and finally we'll finish up with angle theta. Now we're starting to fill in for the remaining values for the entire circuit. First thing on the agenda, let's calculate the value of current for the entire circuit. We're going to use Ohm's law. I total will be equal to the applied voltage divided by the value of impedance, which was one of the first things we had calculated. Or the second, pardon me, or the second. So, 115 volts divided by 54.23 ohms, going to give us, as a result, or a total of 2.12 amperes rounded to 2 decimal places. Now, while we're at it, this is already in the calculator. Why don't we just jump to step 8? You could use this using Ohm's law, or we could use the trig formula. I'm used to doing the trig formula. I find it maintains a higher level of accuracy. So VA is equal to B squared plus var C squared square root. We'll input the values we've calculated. 209.59 watts plus 124.2 var C squared can't forget that square root. And once you've executed this calculation in a calculator, you should have for an answer 243.63 VA, which stands for volt amperes. So I'm going to take a walk down, I'm going to input this, and we're going to wrap this up really quickly. Well, we're making a lot of great progress. Now, all that remains is, let's calculate power factor and angle theta. Step number 9, calculating the circuit efficiency, or in other words, the power factor. I may have covered this previously, but I wanted to kind of put this on somebody's radar. People who are consulting textbooks will find that there's a whole host of formulas that could be used in this application. Personally, I like using this one because I always remembered it as being the ratio of true power to apparent power, but it goes deeper than that. This formula, it does not matter if I am working with a series or parallel circuit, the formula stays the same. If we look at these formulas right here, they are only applicable to a parallel circuit. If you try using this formula, well, for a fact, in a series circuit, the current's the same. So you can't use this formula in a series circuit. Same thing applies here. In this context, the value of impedance is lower than the value of resistance. And if you flipped it, it would work in the series circuit. But the opposite holds true for the parallel circuit. Too many details to remember, too easy to make a mistake. And a mistake can cost you points on a test. And we want to avoid that. That's why I've always advocated this formula. And it's for only that reason. I don't like remembering a whole ton of formulas. I just go with what works. P over VA, the ratio of true power to apparent power. So I'm just going to erase this. And let's input those values. So what were our values? Well, 209.59 watts divided by 243.63 VA. As a result, you're going to get this long number. Let's see here. We'll write it over here. Power factor is equal to 0.860279932. Now, obviously, we're going to have to multiply this by 100 in order to get the expression as a percentage. Or you could do as I do, is I'll just move the decimal 2 spaces to the right, and my expression will be 86.0. Oh, actually, you see the 7? So this is going to have to be rounded up to a 3. And power factor is equal to 86.03%. Now, the only thing that remains is to calculate angle theta. I'm just going to scooch down over here, and we'll get that done. Step 10. Solve for angle theta, which is the cosine angle theta is equal to your power factor. Of course, we've got to manipulate this. We want to isolate for angle theta. It's equal to your power factor, and then we would put down negative cosine. So we're just going to use the decimal value, which, oddly enough, is we have, oh, sorry, it's out of frame. But we're going to use the decimals that we had in the calculator. So angle theta is equal to 0.860279932. 0.8603, and then we would, as an operation in a calculator, all I would do is just put the negative cosine function, and angle theta as a result will be 30.65, sorry, 65 degrees. So I calculated everything. The only thing that remains now is to just put this into our chart, and then we're going to move on to explaining what is the voltage and current relationship when we have an RC parallel circuit. So we filled in all of our missing values for the circuit. Now, all that remains is to go and draw in the voltage and current relationships on our charts and define what they are, both in a graphic form and in a written form. So meet me down there. Here we're dealing with the voltage and current relationship across the resistive load module. It is said that in a purely resistive circuit, voltage and current are in phase with one another. So it doesn't really matter if it's a parallel circuit or a series circuit, because we're going to draw it the exact same way. With the voltage waveform, my current is going to be basically starting at the same point. It will rise in unison. It will collapse in unison. It will cross over at the same point and will follow into the negative alternation and continue the same trend. We're going to identify it if you're using the same color of marker, and not like me where I've got two different colors that we can see. And we're also going to write it out that voltage and current are in phase with each other, and angle theta is equal to 0 degrees. And it doesn't matter if you say current and voltage are in phase with one another, because of the fact there is 0 phase angle difference. The logic, or from a grammatical point of view, it works both ways. Now, let's move on to that last branch, the capacitive branch. Looking at the voltage and current relationship for the capacitive branch of this circuit, for this parallel circuit, we've got the voltage waveform drawn in because it is a fixed value. And we know for a fact that capacitors naturally oppose a change of voltage. And it can be said that the current leads the voltage. In this case here, if I was to use that logic, that means that my current is actually going to be at a higher value, where I'm at the 0 point with my sine wave for the voltage. Current's going to start up here in the positive alternation, and that there is a 90-degree phase angle difference. That means then, if I was to bisect this for 180 degrees, about halfway to 70 and 90. That means then that my current's going to start, and let's say if the peak's right about here. Well, it's going to start up here, go down into the negative alternation. It's going to peak at 180 degrees and then collapse at 270 and continue on the same trend even at 360 degrees. We're going to identify it. Also, we're going to spell it out, that current leads the voltage, which is stationary, by 90 degrees, and whoops, it is not a series circuit, track of things here. It's too late in the day. And a parallel circuit. Oof, avoided a catastrophe there. Thank God I caught myself. So current leads the voltage by 90 degrees in a parallel circuit. And I've mentioned it before. You need to add that to give the reader context. Why is the current leading? Oh, it's a parallel circuit. Perfect. It makes sense. The logic is there. So we're going to move on from here and we're going to solve for the entire circuit. So stay tuned. Here we have the RC parallel circuit. This graph represents the entire circuit and it's represented by the letter Z. Now we calculated the angle theta as 30.65 degrees. I've also taken the liberty of drawing in the voltage waveform. We are working with a parallel circuit, and one of the rules that govern doing calculations with a parallel circuit is that the voltage across each branch will be equal to the applied voltage. Simply stated, the voltage waveform in a parallel circuit is going to be the fixed waveform, or it's a constant. It will always be in the same location if I was to use an oscilloscope to examine this. And it is the current waveform that changes in relation to the fixed or stationary voltage waveform. Because of the fact we've calculated a phase angle difference of 30.65 degrees, that's going to be fairly easy to draw in. Now, we got to remember one thing as well. Capacitors are known for resisting a change in voltage. And that means then, and we've seen this in certain textbooks, they'll make the statement that capacitors oppose a change of voltage and that current will be leading. This case is true. When the voltage waveform is at the 0 point here, that means that my current is actually going to be in the positive alternation. It'll be leading by that 30.65 degrees. So if this is 180 degrees, halfway represents 90, a quarter cycle. Well, if I was to break this up into 3 equal parts, right here, this would represent roughly 30 degrees. I'm going to start here, go into the negative alternation, and cross over at roughly the same distance to maintain that phase angle difference, and continue on. I'm going to label this waveform, and we're going to spell it out. That current leads the voltage by angle theta, which in this case is 30.65 degrees, in a parallel circuit. It is important that we mention what type of circuit that we're dealing with. We need context. Why is the voltage leading? It's because, pardon me, I meant to say that the current is leading because of the fact that you're in a parallel circuit. If it was a series circuit, the current doesn't move. It's the current waveform that is stationary. So it's a really important piece of information to add to any of our descriptions or our statements. I hope that today's video has provided you with some useful information and some strategies in how to solve for the values that are missing in an RC parallel circuit. Until next time, please stay safe.